students, welcome to Sunil's tutorial. I'm Sunil Medwani and today we'll be doing this chapter called as ionic equilibria. Let's see this. We're going to do something called as common ion effect. What do we understand by common ion effect? First let's write the definition of common ion effect. What is common ion effect? It is the phenomena of suppression. It is the phenomenon of suppression of degree of dissociation of a weak electrolyte by adding a strong electrolyte containing a common ion. It is the phenomenon of suppression of the degree of dissociation of a weak electrolyte it is the phenomenon of suppression of degree of dissociation of a weak electrolyte by addition of a strong electrolyte containing a common ion. Containing a common ion. Right? That is what is called as common ion effect. Now let me try to explain this to you. Let's consider a weak electrolyte, acetic acid, is dissolved in water. Consider a weak electrolyte acetic acid dissolved in water. If a weak electrolyte is dissolved in water, then equilibrium will exist between the unionized acetic acid and the ions that have been dissociated. Arrhenius theory. Once you dissolve in water, it will dissociate, and once the dissociation is over, then there will be an equilibrium between the dissociated molecule and the undissociated molecules. So I can say therefore an equilibrium exists between the unionized molecules and the dissociated ions. Right? Now, since it's a weak electrolyte, since the reaction is a reversible reaction, I can apply Le Chatelier's principle to it. Since the dissociation reaction is reversible, since the dissociation reaction is reversible, since the dissociation reaction is reversible, I can apply law of mass action and Le Chatelier's principle. By law of mass action and Le Chatelier's principle, I can say that acetic acid will dissociate reversibly to give you acetate ions and hydrogen ions. Law of mass action. Dissociation constant of the acid is active mass of the product upon active mass of the reactant. Right? Now, let us assume that a strong electrolyte having a common ion is added to this. Right? Now, a strong electrolyte let us consider sodium acetate. Sodium acetate. That's CH3CONA. So your strong electrolyte sodium acetate containing acetate ions is added to the solution. See, you can see the common ion is the acetate ions containing acetate ions is added to the solution, right? In which case, since it is a salt, it will undergo complete dissociation. Sodium acetate undergoes complete dissociation. It undergoes complete dissociation. Sodium acetate dissociates completely to give you acetate ions and sodium ions, right? Now, since acetate ions are common ions, that is, they are present both in acetic acid and sodium acetate, the concentration of acetate ions will be increased. Since acetate ions are common ions, therefore their concentration is increased, right? Now, in order to maintain, see, the value of, in this equation, guys, see this, in this equation the value of acetate ions will increase. Now we know that Ka is constant. If I want to maintain Ka constant, if the value of numerator has increased, to keep the fraction constant, the value of denominator should also increase. The value of denominator will increase when I have more acetic acid. More acetic acid will be formed only when acetate ions recombine with hydrogen ions. So I'm doing reverse of dissociation. I'm suppressing the dissociation. Ideally, acetate and hydrogen ions should have separated out. But to keep Ka constant, they are going to combine with each other again, right? What am I doing? I'm suppressing the dissociation, and that is what is called as common ion effect. Why is the dissociation being suppressed? Because of the presence of the extra acetate ions that have come from sodium acetate. Fine, do we get this in here? Let's write this down. In order to maintain constant value of Ka, constant value of Ka, the concentration of acetic acid molecules increases. The concentration of acetic acid molecules increases, right? Thus, according to Le Chatelier's principle, the equilibrium of acetic acid is shifted towards left. According to Le Chatelier's principle, the equilibrium of acetic acid is shifted to left. Right? If it is shifted to left, that means the dissociation of acetic acid is decreased due to the addition of sodium acetate. Thus, the dissociation of acetic acid is decreased due to the addition of sodium acetate, right? And this is known as common ion effect. Right? So do you understand common ion effect? Right? So in common ion effect, what are you going to do? You are going to suppress the degree of dissociation of a weak electrolyte You're going to suppress the degree of dissociation of a weak electrolyte by adding a strong electrolyte having common ion in it. You're going to suppress the degree of dissociation of a weak electrolyte by adding a strong electrolyte having a common ion in it. Right? Do we get this thing now? Where do I use common ion effect? Application of common ion effect. First, in purification of common salt. The first application is it is used in the purification of common salt. Now, impure common salt, that is your sodium chloride, which is obtained from seawater, on evaporation contains impurities like potassium chloride, magnesium chloride, right? Now, in saturated solution, I can say that impure common salt obtained from seawater contains by evaporation contains impurities like potassium chloride and magnesium chloride, right? Now, in saturated solution of sodium chloride, in saturated solution of sodium chloride, the following equilibrium exists. Equilibrium exists. Sodium chloride, solid, dissociates in solution form to give you aqueous sodium ions plus aqueous chloride ions. Simple. When I dissolve sodium chloride in water, I'll get sodium ions and chloride ions. Sodium chloride dissolved in water will give you sodium ions and chloride ions. Apply law of mass action to this. I can say by law of mass action, law of mass action. If I apply law of mass action, I can say K is active mass of sodium into active mass of chloride upon active mass of sodium chloride. Right? Now, these impurities can be removed if removed, and common salt can be purified by passing hydrogen chloride gas on saturated solution of impure sodium chloride. These impurities can be removed and salt can be purified by passing HCl gas over saturated solution of sodium chloride. If I pass HCl gas, HCl in gaseous form comes in contact with water, it's converted into HCl in aqueous form, which dissociates to give you hydrogen ions and chloride ions. Right? Now, as per Le Chatelier's principle, as a result, what will happen? The concentration of chloride ions will increase, and by Le Chatelier's principle, the equilibrium of sodium chloride will shift to left. I can say that according to Le Chatelier's principle, equilibrium of NaCl shifts to left right? And shifts to left. Therefore, the solubility of sodium chloride is decreased, and thus pure sodium chloride is precipitated. So, on evaporation, the salts will evaporate out. Sodium chloride, since I have suppressed the dissociation of sodium chloride, it will not evaporate out. It will remain in salt form there, and the remaining will dissociate and will evaporate with water. Right? The solubility of NaCl is decreased, and hence pure NaCl is precipitated. Fine. So that's the first part. Next, another application of common ion effect is salting out of soap. Now, soap are sodium salts containing higher fatty acids. Soaps are sodium salts containing higher fatty acids. Right? The soaps are obtained by a process of saponification in the form of solution. Soaps are obtained by the process of saponification, right, in the form of solution. Right? For example, any fat or oil reacts with sodium hydroxide and you boil this, you will have hydrolysis taking place where the fat or oil will react with water to give you a sodium salt RCOO Na and glycerine. Right? This is going to be your soap. Right? Now, in saturated solution, what will be the equilibrium of soap? In saturated solution, if I consider a saturated solution of soap, the following equilibrium exists. Exist, that is RCOONA will dissociate to give you RCOO ions plus sodium ions. Right? This is solid soap. This is soap in the form of solution. This is solid soap. This is soap in form of solution. Right? Now, if a small amount of sodium chloride is added to this, if saturated solution of sodium chloride is added to soap solution, then in that case what will happen to the concentration of sodium ions? The concentration of sodium ions will increase, then concentration of sodium ions increases, right? Now, as a result of this, the solubility of soap decreases. That means it will, you will have suppression of the dissociation, therefore its solubility will decrease. So I will say that therefore solubility of soap decreases, right? And Thus, NaCl precipitates soap back into solid soap form. Therefore, NaCl precipitates soap into solid soap form. Right? So, thus the solubility of soap is decreased. Otherwise, as soon as you put soap in water, it should dissolve completely, but it does not dissolve because of the presence of salt. Fine, do we understand this? So, do we understand common ion effect? Next, let us understand what is buffer solution. What do we understand by buffer solution? A solution that has a definite pH and which resists a change in pH when a small amount of acid or base is added to it is called as a buffer solution. Right? Yes, you want to ask it? Right? What is a buffer solution? A solution definition. A solution which has a definite pH. A solution which has a definite pH and which resists the change in its pH when by addition of small amount of acid or base is known as buffer solution. So, a buffer solution is the one whose pH does not change very easily. Right? Now, what are the different types and preparations of buffer solution? What are the different types of buffer solution? Now, how do you prepare a buffer solution? A buffer solution is prepared by mixing either a weak acid with a salt of strong base or a weak base with a salt of strong acid. Right? I can say that buffer solution is prepared by either mixing weak acid with salt of strong base or weak base with salt of strong acid. Right? Or by dissolving a single salt of weak acid and weak base in water. Or by dissolving salt of single weak acid and weak base in water. Salt of single weak acid and weak base in water. That's how you prepare a buffer solution, right? Now, since it is prepared by salt of weak acid and salt of strong base and weak base and salt of strong acid, there are different types of buffer solution. Either you can have an acidic buffer, basic buffer, or a neutral buffer, right? The types of buffer solution are buffer solution. First one is acidic buffer. Second, basic buffer. Third, neutral buffer. right? These are the three different types of buffer solutions that you have, right? Now, what do we understand by acidic buffer? What is an acidic buffer? An acidic buffer is prepared by dissolving a mixture of weak acid with a salt of strong base. The pH of this buffer solution is always less than 7, right? Prepared by mixing weak acid with salt of strong base has pH less than 7. Right, that's your acidic buffer. Next, the second is basic buffer. Right, what is a basic buffer? It is prepared by dissolving a mixture of weak base with a salt of strong acid and its pH is greater than 7. Right, prepared by mixing weak base with salt of strong acid has pH greater than 7. Right? Do we get this in clear? Right. The third is neutral buffer. Right? Can say this? The third is neutral buffer. Now, what is a neutral buffer? A neutral buffer is prepared by dissolving a salt of weak acid in weak base and it has a pH approximately equal to 7. Prepared by dissolving weak acid, salt of weak acid in weak base, dissolving salt of weak acid and weak base has pH approximately equal to 7. Right? Now, question. I'm going to add acid to a solution. Why is it that the solution does not turn acidic? Or if I add base to a solution, why is it that the solution does not turn basic? Let's see the mechanism of buffer. First, let's consider an acidic buffer solution. Let's consider the mechanism of acidic buffer solution, right? An acidic buffer solution, as I already told you, is prepared by mixing a weak acid with a salt of strong base. So, I can say that an acidic buffer is a mixture of weak acid and salt of strong base. Right? Let's consider that I mix acetic acid with sodium acetate. Acetic acid, that's my weak acid, and salt of strong base, sodium acetate. Right? Now, the salt of strong electrolyte will dissociate completely while the weak acid will be slightly ionized. Right? The salt of strong acid will dissociate completely while the weak acid will be slightly ionized. Right? Once I have this, I can say that the ionization can be represented as follows. be represented as follows. You have acetic acid will be ionized to give you, this is my weak acid, will ionize to give you acetate ions and hydrogen ions, right? And sodium acetate, CH3CONA. This is salt of strong electrolyte. Salt of strong electrolyte will dissociate completely to give you acetate ions and sodium ions, right? Now, all this is already present in the solution. Now consider case 1. Right, case 1, when small amount of hydrogen ions are added to it or small amount of acid is added to it. When small amount of strong acid containing H plus ions is added. Right? Now when acid is added to it, the added acid, that is your H plus ions, will immediately combine with the acetate ions. The extra H plus ions that will be present will immediately combine with the acetate ions. Question: so why will they combine? Because of common ion effect. Common ion effect, because of adding this salt of strong electrolyte, the concentration of acetate ions is very high. So as soon as you put hydrogen ions, then those hydrogen ions will combine with the extra acetate ions, right? So I can say that the added acid, that is acid, when I say acid I mean hydrogen ions. The added acid combines with acetate ions, and are neutralized, right? Hence the pH of the solution remains constant. Hence pH of solution remains constant, right? So the acetate ions will combine with the hydrogen ions from the acid. This is acetate ions combine with added acid. This is your added acid, right? Neutralization takes place to form acetic acid, CH3COH. You have neutralization, right? That is the reason when you add acid to a buffer solution, its pH does not change, right? This, do you understand this? So the capacity of the buffer solution which resists a change of pH even on addition of strong acid is called as reverse acidity. This phenomena is called as reverse acidity. Okay, the capacity of buffer solution, which resists the change in pH even on addition of right, even on addition of strong acid is called reverse basicity. Fine, do we get this? Now This was when acid is added to a buffer solution. What if a base is added to a buffer solution? Case 2. When a small amount of strong base, when a small amount of strong base containing OH ions is added to the solution. Now in this case, the OH ions will immediately combine, the added base will completely combine with acetic acid and will neutralize it. Acid base gives you salt and water, right? So in that case I can say that the added base will combine with acetic acid, molecules and get neutralized. Will combine with acetic acid molecules and will get neutralized. Fine, do we get this thing here? So as a result, since it is going to get neutralized, the pH will not change, the pH will still remain constant. I can say hence the pH of the solution remains constant. Right? Let's see the equation for this. Acetic acid will combine with hydroxyl ions. This is your acetic acid. Will combine with hydroxyl ions. This is your added base to give you acetate ions and water. This is again neutralization. So you have neutralization reaction taking place again, right? This capacity of the buffer solution which resists a change in pH, this capacity of buffer solution which resists the change in pH, resists the change in pH on addition of strong base is called reverse acidity. Right? That's how an acidic buffer works. Right? Okay, we'll stop this here for the day. Thank you very much.